What you're looking at here is a very simplified version of how an artificial neural network makes decisions. This is called a rectified linear unit multilayer perceptron, a type of classification neural network. Each circle you see here represents a neuron, inspired by the way our brains work. The first layer on the left takes in the picture, in this case 784 little boxes, each representing a pixel from the handwritten digits. You can think of this as our input. The neurons in the middle are the network's thinking layer. They take what they learned from the pixels and combine that information in many different ways. The lines between the neurons are called connections. They have a strength called weight that determines how much influence our neuron has on another. In this visualization, the colors of the lines show whether the influence is positive or negative, and how strong it is. Each neuron's value is calculated simply by adding the weighted sum of all connections leading to it, including bias. Deep learning is fascinating because the hidden layers work like a black box. We don't fully understand exactly how each neuron thinks, but together they form a system that somehow works really well. On the right is the output layer. It has 10 neurons, one for each possible digit from 0 to 9. The neuron with the highest value is the network's prediction. What's special here is that you're seeing the training happen in live. Every frame, the network sees a new example, makes a guess, and then adjusts all the weights and biases to improve. Over time, you'll see how the connections change and guesses get more accurate. So in short, we feed in images of handwritten numbers, and the network processes them through layers of neurons, and the result is a computer that can read handwriting, just by learning from examples. This is exactly the same process used in big real-world AI models, just with millions more neurons and connections. Now let's dive into the code. First of all, I needed to declare 3 types of objects. The first one is a box, which I'm going to be using to draw all the 784 pixels on our screen. So it takes into the position, and we have to declare a Pygame rectangle object, the top left position, and the width and length of the rectangle. In this case, it's the box length. And then it also takes into account the value parameter, which is between 0 and 1. And we're going to find the color by multiplying that value by 255. So if the value is 1, then completely red, 25500, and if it's not, it's just going to be black, and 000. The next class is just a neuron, and all it has is the position values. Then we have the connections class, which is connection between 2 neurons, so it takes in that. And you can see I wrote this line right here, which returns a list of Pygame colors, which I'm guessing is listed by gradient. And it's pretty handy, I guess, to visualize the connection, the weights. And I actually wrote a little Python notebook here to help you visualize it without the graphics, like the rendering stuff. So just the PyTorch machine learning. First of all, load the CSV file in and separate the labels from the features. I used scikit-learn's train test split to split the data into 80% training and 20% testing data. Then convert them to PyTorch tensors and declare a PyTorch data loader. Next, I defined a simple multi-layer perceptron for the MNIST data. I used 784 for the first input layer, and 128 for the first hidden layer, 64 for the second hidden layer, and 10 for the output layer. It's time to train this model and evaluate the results. Here I added the option to manually choose an index, and it will automatically draw the data point at that index for you and what number the model thinks it is. I also decided to plot the error and accuracy over time. Okay, so after graphing it, I decided to see how well it would perform for the testing dataset. And this is the testing target, the target for the testing data. So everything looks correct so far. And we got 93% accuracy, which is pretty good, I think. Alright, so now to actually implement that into the main file, I basically copy and paste the setup, and I would say the hardest part of this project was to set up all the boxes and the connections and the neurons to be rendered on the screen and update them every frame. The code is on my GitHub page, and if you enjoyed this video, please like and subscribe. I'll see you in the next video.